Chapter 4. Biological Food Safety Hazards for Human Food. In developing or modifying a food safety plan, it is important to be aware of the potential hazards that are associated with the food products and processes under consideration. When hazards are understood, preventive measures can be implemented to control those hazards, thus preventing illness or injury. This chapter introduces the definition of the term hazard, discusses biological hazards that are commonly of concern in food processing plants and facilities holding food products, and reviews potential controls for biological hazards. The Preventive Controls for Human Food Regulation defines hazard as any biological, chemical, including radiological, or physical agent that is reasonably likely to cause illness or injury. Biological hazards include pathogenic bacteria, viruses, and parasites. Chapter 5, Chemical, Physical and Economically Motivated Hazards covers chemical, including radiological, and physical hazards mentioned in the definition. Information from this chapter on biological hazards and Chapter 5 is useful for conducting a hazard analysis for a food, which identifies the hazards that require a preventive control. The hazard analysis process is discussed in Chapter 8, Hazard Analysis and Preventive Controls Determination. It is important to understand that, for the purposes of food safety, the term hazard refers only to the conditions or contaminants in food that has the potential to cause illness or injury to people. Many conditions are highly undesirable in food, such as the presence of insects, hair, filth, or spoilage. Economic fraud and violations of regulatory food standards are equally undesirable. All of these defects should be controlled in food processing, however, many times they are not directly related to the safety of the product. Unless these conditions directly affect food safety, they are not included in a food safety plan. The Preventive Controls for Human Food Regulation considers decomposition to be a food safety hazard when biogenic amines or other toxic substances are produced. How a hazard is addressed in a food safety plan depends on both the likelihood of its occurrence in the absence of its control and the severity of the illness or injury that would result if the food is consumed. The difference between a known or reasonably foreseeable hazard and a hazard requiring a preventive control is explained in Chapter 8, Hazard Analysis and Preventive Controls Determination. The current chapter provides a general discussion of biological hazards in food products. A useful source of information on the hazards that may be present in different foods is FDA's Reportable Food Registry. See additional reading. This registry collects information from the food industry and from public health authorities on foods or feed that are likely to cause serious adverse health consequences or death to humans or animals if they are used. Biological hazards represent the primary category of hazards reported through the registry. However, undeclared allergens in food represent about 1/3 of the reports. These are discussed in Chapter 5, Chemical, Physical and Economically Motivated Hazards. The Centers for Disease Control and Prevention, CDC, surveillance data on foodborne disease outbreaks, i.e., 2 or more people become ill from consuming the same food item, are illustrated above. The number of illnesses reported is just the tip of the iceberg because many foodborne illnesses are not reported to CDC. However, the data are useful to understand the types of hazards that are likely to cause illness. Biological hazards, including bacteria, viruses, and parasites, are the most frequently reported hazard group associated with foodborne illness in the U.S. Chemical agents are also reported, but as you can see, reported numbers are much lower than those for biological hazards. Food allergen reactions may not be captured in these CDC data because an outbreak requires 2 or more people to be ill from the same food. Allergenic reactions are sporadic and likely involving one person at a time. CDC surveillance systems do not report physical hazard outbreaks. CDC surveillance data include confirmed and suspected foodborne illnesses that are reported by states. These numbers are just the tip of the iceberg and do not include adjustment factors for underreporting. The CDC estimates that 1 in 6, or 48 million, people get sick from eating food every year in the U.S. and 3,000 die. Most biological hazards belong to a group of living life forms that are too small to see with the naked eye, called microorganisms. Microorganisms are present in air, dirt, water, skin, hair, animal fur, plants, and numerous other sources like saliva and air expelled with coughs and sneezes. Microorganisms are classified into various groups including bacteria, viruses, protozoa, yeasts, and molds. Prion are the agent responsible for mad cow disease, or in technical terms, bovine spongiform encephalopathy or BSE, and similar diseases in other animals including certain types of game. Prion are not covered in this course, but see FDA's Bad Bug book attached in the chapter resources if you process game. Many microorganisms are beneficial. Certain kinds of yeasts, molds, and bacteria help make cheese, sour cream, yogurt, sausage, pickles, sauerkraut, and other fermented products. Particular strains of yeasts are used in making bread, beer, wine, and other fermented products. These microorganisms are intentionally added to foods and they cause no harm. People come into contact with thousands of kinds of yeasts, molds, bacteria, viruses, and protozoa daily without ill effect. In fact, bacteria live naturally on our skin, in our noses, mouths, and digestive tract. They play an important role in digesting our food and are part of a healthy human system. Let's take a look at an important definition. Pathogen, a microorganism of public health significance. 21 CFR 117.3 Definitions. In this course, the term is generally used to refer to microorganisms that cause illness through consumption of food. Bacteria, parasites, and viruses are different kinds of biological hazards. Control strategies are discussed later. Foodborne pathogens, however, may be hazardous to humans under certain conditions. Viruses and bacteria are the most common foodborne pathogens. Many different types of bacteria can cause foodborne illness. Most foodborne virus outbreaks are caused by norovirus, typically in food service settings, but others, such as hepatitis, are also known. Some molds produce hazardous toxins called mycotoxins, which are considered chemical hazards in this course. See Chapter 5, Chemical, Physical, and Economically Motivated Food Safety Hazards. Remember that biological hazards can be introduced into a food product from ingredients and other raw materials, from food processing equipment and environments used to make the final product, and from people handling the product during harvesting or processing. Understanding how biological hazards can behave when they are introduced into a food can help you to determine how best to control them. Foodborne pathogens may cause illness in humans by either infection or intoxication after the food is eaten. Foodborne infections are caused by consuming live pathogens that grow in the body, usually in the intestinal tract, and cause illness. Because growth in the body is required for an infection, considerable time can pass before symptoms occur, typically more than 12 hours and sometimes days or even weeks. In other instances, the high numbers of some pathogens release toxins in the intestinal tract, e.g., Clostridium perfringens and certain strains of Bacillus cereus. The specific infection symptoms depend on the pathogen and the susceptibility of the person eating the food, and can include nausea, vomiting, diarrhea, and sometimes fever. Illness can sometimes lead to hospitalization and even death. Viruses, parasites, and many bacteria of concern in food cause infections. While viruses and parasites cannot grow in food, prevention of bacterial growth is important because the greater the number of pathogens present in a food, the more likely it is that someone will become ill. More information on growth is discussed later in this chapter and in Appendix 4, Foodborne Pathogen Supplementary Information. Foodborne intoxication is caused by consuming toxins produced by high numbers of certain bacteria, e.g., Staphylococcus aureus and certain strains B. cereus, after they have grown in the food. Symptoms from foodborne intoxication usually occur more rapidly than those from a foodborne infection, and illness can occur a few hours after consumption. Prevention of pathogen growth in food prevents foodborne intoxications. Some toxins are not destroyed by heat, so reheating food that was temperature abused does not necessarily make it safe. Many infectious bacteria, such as Salmonella, can present a potential hazard simply due to presence in the food when consumed, whereas other bacterial pathogens require growth to a level that can make people sick. Some knowledge of bacterial pathogens and what it takes to create a hazardous condition in food is important for selecting preventive controls. Because of the diversity of the food supply, it is reasonable to assume that some potentially hazardous bacteria will be present in ingredients and food processing environments. See Appendix 4, attached in the chapter Resources for Foodborne Pathogen Supplementary Information for information on different foodborne pathogens, including symptoms and parameters that can control growth. 3 basic strategies can be used to control bacterial pathogens in food: prevent contamination, kill them, and control their growth. Prevent contamination. Keeping pathogens out of the food can be accomplished through practice of good personal hygiene by food workers, prevention of cross-contamination through effective sanitation practices, and use of a safe supply of ingredients and other raw materials to minimize the introduction of pathogens into the facility and the food. Much of this is managed through GMPs discussed earlier, like personnel practices as well as sanitation. Good agricultural practices and good husbandry practices on farms are also important to minimize contamination of ingredients coming from the farm. Recontamination of products after cooking or other antimicrobial treatments has also caused outbreaks. Because of this, selection of appropriate preventive controls should consider the potential for bacterial survival and reintroduction after cooking or other inactivation processes. Inactivation, killing, and elimination are all terms that refer to reducing pathogens to a level that is unlikely to cause illness. Cooking is frequently used to destroy pathogens. However, other techniques such as irradiation, high-pressure treatments, antimicrobial chemicals, e.g., sanitizers, acidification, ultrasound, and pulsed light may also be applied to food or to food contact surfaces. These techniques must be validated to the specific food and processing conditions to ensure that they control the pathogens of concern in the specific food. For example, for cooking to be successful, the food must reach an adequate temperature for a long enough time to kill the microorganisms of concern. Higher temperatures kill faster than lower temperatures. The required temperature depends on the food, the pathogen of concern, and the time involved. Safe cooking temperatures may be established for certain foods. Other validated time/temperature combinations may also be appropriate. Appendix 4, attached in the chapter Resources Foodborne Pathogen Supplementary Information, provides time and temperature guidance for controlling pathogen growth and toxin formation as well as inactivation of Listeria monocytogenes. FDA's Model Food Code provides safe cooking time and temperature combinations for a variety of foods. FDA's Dairy Hazards Guide also provides safe cooking temperatures for certain products. Other validated time and temperature combinations may also be appropriate for certain foods. Bacterial hazards can be classified as spore-formers and non-spore-formers. Bacterial spore-formers are notable for their ability to produce spores that can survive harsh conditions that destroy other pathogens. In the photo above, the bright ovals are heat-resistant Bacillus cereus spores, and the larger, dark rod-shaped bacteria are B. cereus in its vegetative state. Spores are not hazardous as long as they remain in the spore state. Unfortunately, spores are very resistant to heat, chemicals, and other treatments that would normally kill vegetative forms of both spore-formers and non-spore-formers. When spores survive a processing step designed to kill vegetative bacteria, they may become a hazard in the food if they are exposed to favorable conditions that allow germination and growth as vegetative cells. This can be particularly serious when a processing step has removed most of their competition. The process steps used to kill spores are often much more severe than those necessary to kill vegetative cells because spores are more resistant. Some vegetative cells are more resistant than others to inactivation methods. Thus, it is important to understand the potential pathogens of concern in a specific food and to demonstrate, through validation, discussed in Chapter 13, verification and validation procedures, that the controls that you apply actually control these hazards. It is also important to understand if destroying one type of hazard provides an opportunity for other hazards to emerge because competition is eliminated. Keeping microorganisms from growing can be an important control when the process does not kill potential pathogens, e.g., spores, or when products may become recontaminated after a lethal process, e.g., ready-to-eat products that are exposed to the environment after cooking. Preventing growth also may reduce the risk of foodborne disease because some pathogens must grow to a sufficiently high number to present a hazardous situation, such as when toxin production or a high infectious dose is needed to cause illness. Time, temperature, the level of acidity, pH, available water, water activity, the right level of oxygen, atmosphere. The presence of competition by other bacteria and preservative use can all influence growth of potentially harmful bacteria. It can sometimes take bacteria a bit of time to start growing, lag phase, but then under favorable conditions they take off and grow rapidly with one bacterium dividing into 2, 2 into 4, 4 into 8, 8 into 16 and so on, growth phase. Under ideal conditions, some bacteria double every 20 minutes, thus one bacterium can multiply to more than 30,000 in 5 hours and over 16 million in 8 hours. If relevant, toxin formation usually occurs during exponential growth. Growth continues until they run out of what they need to keep multiplying, stationary phase, and then they can start dying off, death phase. Ideally, growth will be prevented due to the nature of the food itself or through application of preventive controls. Logarithmic scale. A logarithmic, log, scale is used to plot microbial growth because of the rapid increase in numbers. Simply put, there is a 10-fold difference between each unit on a log. For example, a log unit of 2 is 10 times more than a log unit of 1. Similarly, a log unit of 5 is 10 times more than a log unit of 4. For example, 3 log equals 1,000, 4 log equals 10,000, 5 log equals 100,000, etc. Bacteria have certain requirements to live and grow, including food with their required nutrients, the appropriate temperature, water available in the food, a suitable pH, the right atmosphere, and other factors. If conditions are not favorable for growth, some bacteria die while others persist until their growth requirements are met, such as water being added to a dry environment. Improper holding temperatures for food may allow foodborne bacteria to multiply. Very rapid growth of foodborne pathogens can occurring between 77 degrees Fahrenheit to 104 degrees Fahrenheit, 25 to 40 Celsius. The range of temperature that supports pathogen growth varies considerably depending on the specific bacterium, see Appendix 4, and characteristics of the food. Guidelines have been developed for how long food can be held at potential growth temperatures. For example, cooling models have been developed for C. perfringens because of the potential for its rapid growth when cooling soups and sauces. The temperature of the food itself is of primary importance. For example, even if a refrigerator or cooler is at the proper temperature, food placed in it may not cool down rapidly if large containers or insulating layers exist. See Table A4.2 in Appendix 4, Foodborne Pathogen Supplementary Information for Guidelines on the Maximum, Cumulative Time and Food Temperature Combinations for Controlling Growth and Toxin Formations for Foodborne Pathogenic Bacteria. In general, holding food at temperatures between the proper refrigeration temperature for your product and 135 degrees Fahrenheit, 57 Celsius, should be avoided. This is the danger zone at which bacterial pathogens can grow. The pH of a food is a measure of its acidity or alkalinity. Foods with a pH less than 7.0 are acidic. The pH of a food can be measured using a pH meter or pH paper. Foods with a lower pH, like vinegar and lemon juice, is more acidic than those that have higher pH, like milk and eggs. A pH below 4.6 prevents the growth of many bacterial pathogens, such as Clostridium botulinum, which is a deadly pathogen. However, some pathogens can grow below 4.6, depending on the food, temperature, and other factors. See Appendix 4, Foodborne Pathogen Supplementary Information. For example, Salmonella, the most common bacterial hazard associated with foodborne illness, has been reported to grow in environments with pH as low as 3.7 under otherwise optimum conditions. While a low pH may prevent bacterial growth, some pathogens can survive. Do not assume that a low pH will necessarily kill a pathogen. All forms of life require water to grow. Water activity, is a term used to describe the availability of water, free moisture, in a food. Pure water has a water activity of 1.0. Adding substances such as salt, sugar, and other food ingredients can reduce the availability of water for microbial growth. Think about seawater. Different species thrive in the ocean than in a freshwater lake. The same is true for microorganisms. Many fresh foods have R values above 0.96, which supports the growth of pathogens. There are also many dry foods with R values below 0.6, which inhibits pathogen growth, although some bacteria, such as Salmonella, can survive for long periods of time. In between, there is a range of foods that may have R values that support growth of some pathogens. Growth of pathogenic bacteria stops when the R is less than 0.86. Staphylococcus aureus is the only foodborne pathogen that grows below 0.92. Details on our limits for specific pathogens are provided in Appendix 4, Foodborne Pathogen Supplementary, attached in the chapter Resources. It is important to recognize that the range of R values for some food categories can be quite broad. Specific measurements are needed for these types of products if R is used as a growth control strategy. For foods that have different components, such as a donut with a cream filling, the pH and R may be quite different in the components. In the donut example, the filling may be acidic and have a high R, while the donut part may have a near-neutral pH and a lower R. The interface between the filling and the donut may be just right for microbial growth, which may be an issue if contamination of the interface is reasonably likely to occur. It's important to understand the definition of water activity. Water activity, a measure of the free moisture in a food, and is the quotient of the water vapor pressure of the substance divided by the vapor pressure of pure water at the same temperature. 21 CFR 117.3. The report Evaluation and Definition of Potentially Hazardous Foods provides information on pH and R combinations that prevent foodborne pathogen growth. See Chapter Resources. Also see Chapter 13, Verification and Validation Procedures. Some pathogens prefer to grow at the concentrations of oxygen present in the air we breathe. Others prefer or even require little or no oxygen before they can grow. Of particular concern for food safety are anaerobic conditions, very low or no oxygen, that favor the pathogen C. botulinum. Changing the packaging to control oxygen levels may change the hazards of concern for a food. For example, creation of anaerobic conditions through packaging can inhibit spoilage organisms and extend shelf life. However, this anaerobic environment and longer shelf life may provide an opportunity for unanticipated hazards, such as growth of C. botulinum. Such changes should be carefully considered, and studies to validate product safety may be necessary. When there is little competition for nutrients, bacteria can reproduce rapidly. Conversely, the presence of other bacteria can inhibit the growth of certain pathogens. For example, production of toxin by Staphylococcus aureus may be suppressed when competitive bacteria are present. Fermented products like yogurt, which have high levels of active cultures, inhibit the growth of pathogens when fermentation proceeds at the normal rate. Preservatives, like nitrite, sorbate, propionate, and benzoate, may slow or prevent the growth of pathogens as well as spoilage microorganisms. The effectiveness of these preservatives depends on many factors. Thus, when relying on preservatives to control pathogen growth, validation, see Chapter 13, Verification and Validation Procedures, is essential to ensure efficacy. If not used at approved concentrations, some preservatives may be chemical hazards. For many foods, bacterial growth is often controlled using one or more of the factors described above to make the food unsuitable for pathogen growth. Some preservation methods remove water, making this essential component unavailable to bacteria. For example, baking bread or crackers removes water from the food. Acidification is also a common method of preservation, for example, pickles, as is refrigeration, which slows growth, or freezing, which prevents pathogen growth entirely. Combinations of factors such as pH and OM may inhibit organisms at levels where the individual factor alone would not. Some people refer to this as the hurdle approach. Use of a combination of factors frequently requires expert knowledge to develop a stable combination. Salmonella is one of the most common foodborne pathogens. The slide above illustrates information that is available in Appendix 4, Foodborne Pathogen Supplementary Information. Salmonella is among the most common causes of bacterial foodborne illness and can be an environmental pathogen. The infection causes diarrhea, fever, abdominal cramps, and vomiting. Occasionally, Salmonella may cause bloodstream infections and death. Severe cases may also result in reactive arthritis. Foodborne illness symptoms generally appear 12 to 72 hours after eating contaminated food. The intestinal tract of animals is the primary source of Salmonella, thus raw animal products, meat, poultry, eggs, milk products, are frequently associated with outbreaks. Because Salmonella survives well in many environments, many foods have been associated with outbreaks, such as yeast, coconut, sauces, cake mixes, cream-filled desserts, gelatin, peanut products, chocolate and cocoa, and soy ingredients. Fresh fruits, vegetables, and nuts can be contaminated during growing if good agricultural practices are not applied. Salmonella is easily killed at traditional cooking temperatures in high moisture environments, grows with or without air, grows best at human body temperature, grows very poorly at refrigeration temperatures, and does not grow above 115 degrees Fahrenheit, 46 Celsius. Unlike most other pathogens, some strains of Salmonella can grow at a pH as low as 3.7 under otherwise optimum conditions. It survives well in frozen and dry foods, as well as in dry processing environments. It can be very heat resistant in a dry state. Attempts to wet clean dry processing environments have been shown to spread contamination and increase the risk of product contamination because of growth in environmental niches like cracks and crevices that cannot be reached by sanitizers. It is best to keep dry environments dry when Salmonella is a potential concern, since moisture can allow it to grow. You really need to know your enemy. See Appendix 4, Foodborne Pathogen Supplementary Information for similar information for other bacterial pathogens. Understanding the characteristics of the pathogens of concern for the foods that you produce is important to select appropriate preventive controls. Like other microorganisms, viruses are common in the environment. They are very small particles that cannot be seen with a light microscope and cannot reproduce by themselves. Viruses can persist in foods without growing, because they need no food, water, or air to survive. Those associated with foodborne illness can survive freezing and do not cause spoilage. Viruses cause illness by infecting living cells and reproducing inside the host. Viruses grow only in a suitable host, and only certain viruses infect humans. Infected people are the primary source of foodborne viruses. Foodborne viruses of concern can survive in human intestines, contaminated water, frozen foods, and environmental surfaces for weeks or months. The most common foodborne viral hazards are norovirus, the leading cause of foodborne illness in the U.S., and hepatitis A virus. Other viruses, such as rotavirus, may occasionally be associated with foodborne illness, and more may be identified in the future. While the vast majority of viral outbreaks occur in food service settings, outbreaks have been associated with processed foods. For example, a large norovirus outbreak occurred in Germany that was associated with frozen strawberries imported from China. Viruses can infect consumers through contact with infected people or contaminated food or water. People who are ill from a viral illness can shed viruses in very high numbers in vomit or feces. Even when they recover from the illness and no longer show outward signs of illness, people can still shed the virus in saliva and feces. Transmission of viruses to foods is usually related to poor employee hygienic practices such as improper hand washing or working while actively shedding viruses. Therefore, prohibiting people with viral illnesses from coming into direct contact with food reduces the chance for foodborne transmission of viruses. Person-to-person transmission is very common for the viruses associated with foodborne illness outbreaks, which is another reason for requiring ill individuals to stay home from work. It prevents other workers from contracting the disease and spreading it to food. Outbreaks have been traced to foods exposed to inappropriately treated water. This may be rare in developed countries, but may be a concern in certain regions of the world. Thorough cooking is also an effective control mechanism, and most foods associated with viral foodborne outbreaks are ready to eat. There is some evidence that high-pressure processing may also be effective in reducing the risk of transmitting foodborne viruses, and exploration of validated processes for specific foods is necessary for this control strategy. Norovirus is resistant to sanitizer concentrations used for food contact surfaces. An EPA-registered disinfectant with claims against norovirus should be used. A general list of these products is available through EPA, and the term norovirus or Norwalk virus will appear on an EPA-registered disinfectant label. Carefully follow manufacturer's label instructions for use. If used on a food contact surface, rinse the surface after treating and follow with a sanitizer at the appropriate concentration before using the equipment. Like viruses, foodborne parasites do not grow in food. While foodborne parasite outbreaks are reported much less frequently in the U.S. than viral or bacterial agents, it is important to recognize potential issues and sources and control for these agents. Parasitic foodborne and water-associated disease are more common in countries with poor sanitation. Appendix 4 provides brief descriptions of the foodborne parasites listed above. Some parasites may be transmitted through food or water that is contaminated by fecal material shed by infected hosts or by consuming infected animal tissue. Methods of preventing transmission of parasites to foods by fecal contamination include good personal hygiene practices by food handlers, elimination of insufficiently treated animal waste to fertilize crops, proper sewage and water treatment. Consumer exposure to parasites depends on food selection, cultural habits, and preparation methods. Parasitic infections are normally associated with raw or undercooked foods because cooking procedures that destroy pathogenic vegetative bacteria also kill foodborne parasites. In specific instances, freezing can be used to destroy parasites in food. Freezing and thawing cycles can prevent infectivity of Giardia, Cryptosporidium, Cyclospora, Trichinella spp. And seafood-related parasites, which are not covered in this training. Certain pathogenic bacteria, viruses, and parasites are closely associated with particular foods. Control of these pathogens should be considered when processing these foods and foods that contain them as an ingredient. If you process food products, it is important to have a basic understanding of the most common foodborne pathogens, including where they come from, source, how they contribute to foodborne illness, when they are concerned, and what preventive controls can minimize the risk they present. The table above is not a complete list of pathogens that may be associated with various foods. It does list some of the pathogens that should be considered when performing a hazard analysis for these particular foods. The hazard analysis process is covered in Chapter 8. Although it is not necessary to list all possible pathogens that could be associated with a specific food, you should take into account those pathogens that are known or reasonably foreseeable, either because of their frequency of occurrence or because of the potentially severe consequences of their presence. Consideration of the different pathogens allows you to design a food safety system that will control all of the different pathogens. This is usually done by designing the control procedure to be effective against the pathogen that is most resistant to the procedure. For example, if you decide to use cooking or pasteurization to destroy pathogens, setting the cook time and temperature to kill the pathogen that survives at higher temperatures for longer times than the other pathogens would also kill the other pathogens, although spore-forming pathogens may require different controls such as refrigeration. Another reason for considering individual pathogens is that if a new pathogen is identified as a concern, and this happens from time to time, you will know if your plan has considered it. In addition to pathogens normally associated with particular foods, there are pathogens associated with certain practices. For example, the spore-former C. botulinum grows only under anaerobic, low oxygen, conditions, while the vegetative, growing, form of this pathogen is sensitive to heat. The spores are highly resistant and survive most cooking processes. A process that employs vacuum packaging generates anaerobic conditions that favor growth and toxin production by C. botulinum when temperature and other conditions are suitable. As previously discussed, biological contamination of food products typically comes from one of three different sources: 1. Ingredients, 2. The processing environment, including equipment, or 3. People. Controls are needed to manage the hazards introduced from these sources. For example, sometimes ingredient hazards can be reduced to a safe level by using process controls such as a cooking procedure, or maintained at a safe level using temperature control. However, not all products receive a cooking step or temperature control, and cooking may not be effective against some pathogens. In many cases, the preventive control for the hazard is done by the supplier. In these cases, if an ingredient has a history of being a potential source of a particular hazard, a supply chain program may be required. This is determined through hazard analysis. See Chapter 8, Hazard Analysis and Preventive Controls Determination. The processing environment, which includes equipment, is a potential source of environmental pathogens and cross-contamination. Cross-contamination occurs when pathogens are transferred from raw products to processed or ready-to-eat (RTE) products. Direct contamination can occur when raw product is stored in a cooler with condensate dripping on processed product. Indirect cross-contamination occurs when a surface is used for both a raw product and RTE product, such as putting cooked product back into the raw product container. Cutting boards, work tables, tools, and utensils, particularly those with hard-to-clean surfaces, are other common sources of cross-contamination. Cooking a product in package can prevent recontamination, but cooking in package is not possible for many products. Effective sanitation controls, including cleaning, sanitizing, and zoning, are useful to reduce the likelihood of post-process and cross-contamination. An environmental monitoring program could also be used to verify the effectiveness of these controls. These types of controls are discussed in Chapter 11, Sanitation Preventive Controls. People with an illness or infection may potentially contaminate product. Transmission of pathogens by ill employees can typically be controlled when addressed by GMPs and training, which is discussed in Chapter 3, Good Manufacturing Practices and Other Prerequisite Programs. People can also serve as a vector for transmission of pathogens from a raw product to a ready-to-eat product. Effective hand washing procedures are needed to prevent such transfer, and again, this is typically managed by GMPs. Effective training is required to make food handlers aware of these situations so they can prevent these occurrences. In summary, biological hazards can present a food safety risk if not controlled. The severity of the risk depends on a number of factors, including the consequence of exposure and frequency that the hazard is observed with or without controls in place. Preventive controls must be designed, documented, and implemented for all biological hazards requiring a preventive control. Because there are many potential hazards that could be considered in the production of food, it is important to identify those that are of such importance that they must be managed using a preventive approach. This will enable you to focus resources on the most important hazards. The hazard analysis process is an important step to identify those hazards requiring a preventive control. This is addressed in Chapter 8, Hazard Analysis and Preventive Control Determination. Remember the three main strategies to control biological hazards: prevent contamination, kill them, and control grow. Strategies to prevent contamination must address ingredients, people, and the environment as relevant to the product being produced. Complete assurance that you can prevent contamination may not be possible. When killing pathogens is considered, remember that spores are harder to kill than vegetative bacteria, frequently requiring heating under pressure to achieve effective temperatures. This is not feasible for many foods. Finally, preventing growth using time, temperature, pH, water activity, atmosphere, competition, preservatives, or combination of these is important for many foods when contamination cannot be guaranteed. Wow! That was a big chapter. Good job hanging in there. Please be sure to review all the chapter resources and complete all activities and exercises.